My name is Hongyi Wu. I'm a professor and a director of the School of Cybersecurity at Old Dominion University. First of all, I would like to bring greetings from Dr. Luis da Silva, who is the executive director of the Commonwealth Cyber Initiative. He's not able to join us today, but on behalf of the Commonwealth Cyber Initiative, I would like to welcome everybody to join the CCI AI for Security seminar series. So this is the seminar series for the fourth semester, and this is our very last seminar today. Well, CCI is a statewide effort for establishing Virginia as a global center for excellence at the intersection of cybersecurity and the data and cyber physical systems. It's a great honor to host this seminar series. First of all, if you have any questions during the talk, please feel free to type your questions by using the Q&A button, at the bottom of your Zoom window. I will keep most of the questions towards the very end. But if you have a quick clarification question, please feel free to let us know, and we can pose that question to the speaker and let him to answer that question before we move forward. But let me start with introducing our speaker today, Dr. Tim O'Shea. Dr. O'Shea previously worked with the Department of Defense Lab on software in cognitive radio applied research technologies and rapid prototyping. He helped build and lead the GNU radio project. He co-chaired a few conferences, for example, the IEEE Emerging Technology Areas on Machine Learning for Communications. He's an editor for Transactions on Wireless Communication and TCCAN. He co-chaired the IEEE GlobalCom and the IEEE ICC Machine Learning for Communication workshops in 2020. He's a co-author of more than 50 papers with more than 3,000 citations, as well as about 20 patents, primarily focusing on the intersection of wireless communication and machine learning. Well, previously, he was a technical consultant for multiple companies. He has served as a technical advisory board member for programs at NSF, DARPA, Horizon 2020, and DoD programs. He completed his PhD from Virginia Tech ECE department in 2017, and his BS and MS in ECE at NC State in 2007. So on behalf of CCI Director Dr. Da Silva and the entire CCI team, thank you, Dr. O'Shea, for taking your time to give us a lecture today. And without further ado, let's welcome Dr. O'Shea.
Awesome, thank you. Thanks for inviting me to chat with the group today. So let me put up my slides here. Looks like you may need, yeah, there you go. All right, hopefully that's showing up well. So I'm going to talk a little bit about kind of what we've been thinking and looking at in optimizing and securing wireless systems, and specifically around 5G and what's going on as IoT and technologies beyond 5G are I think 6G is becoming more and more common to talk about and acceptable. So I think people are really thinking now about what's going to happen beyond 5G, and so I'm kind of dual-hatted. So I'm up in Northern Virginia at the VT campus part-time, and then I'm also working with DeepSig as the CTO. And so a lot of this work, started at Virginia Tech while I was doing research with the Hume Center and doing my dissertation there. And so everything we'll cover is kind of a mix of work that we did at VT and is ongoing at VT under a kind of a CCI and CIT grant program, and also work that's being done to try to build software capabilities out of it for a number of different applications. So what's the motivation here? If you look at 5G and 6G and all of these IoT systems, really, we're just getting to these massive levels of device density in wireless. So I think the count is today we have something like 20 to 30 billion devices that are in use in cellular, just cellular systems. And carriers are looking beyond people for what will drive the next generation of wireless. So all of the surveys look, asking people, do you want to pay more for 5G? Will you upgrade to 5G? They've not been drastically positive, right? So people don't want to pay more for their wireless service. They want to just continue, but have it continue to improve. So really there's a massive look beyond people towards devices, industrial systems, and other sorts of services that can continue to grow on the wireless network. So I think, we're scaling now way beyond, our traditional cell phones into devices throughout our infrastructure. So the estimate, I think, for 2025, we may be up to 75 billion devices, and then by 2030, the average person on the planet will have something like 15 equivalent devices that may be connected. So, we're talking about really massive numbers of devices in dense urban and in all sorts of environments you could think of. And so this idea of scaling our spectrum usage to very efficient multi-user and very efficient power consumption, these are critical to making all of this work well for everyone. And also really, one of the big things with 5G is trying to vary it, have it be dialable. So if you need extreme reliability or you need extreme low latency, you can deliver these different application requirements to people rather than just have one set of performance that you can meet. So the technologies to get there, that we have the 3GPP standards, 2G up through 5G, and as that's evolving into REL 16, 17, 18, will eventually become beyond 5G. And then there's all of these sorts of IoT protocols. You have Sigfox and LoRa, NB-Fi. There's many different technologies out there, and so we already have many different wireless networks around us operating, and it's really impossible to keep track of. So if you're a government facility or a company that's trying to protect your intellectual property, well, how do you know what data is coming in and out of your building? How will we ever be able to secure any of this, right? Because it's just a massive, complex wireless environment. So these are kind of the really massive needs, is we need to understand, be able to secure these sorts of systems. We need to understand what all is out there and operating in our facilities, and we need to be able to optimize for the multi-user, for the multi-application, and for the really just this dense environment to get the best spectrum efficiency we can. So the problem with getting this efficiency then is that we have a bunch of really nice exact solutions to problems in physics and EM. We have Maxwell's equations and Snell's law, and we have ray tracing and very precise EM propagation modeling tools. But if we want to take, like this urban scenario on the bottom left, or even just a normal kind of house type scenario, well, like, how can we represent this accurately with these models? It becomes this massively complex parameter problem where we needed exact geometries and surface properties. We need to know about what kind of near field effects are happening with all of the different materials in the area. We need to know about interference sources and coupling. So there's so much going on in this environment that we can try to model it with all these exact model-driven solutions, but it becomes a data problem by trying to understand and parameterize and measure all of those things. So modeling all of this in a closed form is somewhat intractable. I mean, it's very hard to model all of these effects accurately. if we want to really have a perfect model for what's going on as our wireless communications propagate through these environments. So it becomes a data problem either way, either through measurement data or through attempts to model environments very, very detailedly. So there's no way to escape this data complexity. I think often people pose this choice between model-driven and data-driven, but if you want an accurate model, it's data-driven either way. It's either measurement or it's more parametric data. So as these systems become much more dense and heavily populated, we cannot ignore all of these effects anymore. If we want to get every bit of spectral efficiency out of our wireless systems, we need to be able to optimize over all these degrees of freedom. So I kind of break this down into these two core problems that will be kind of the two halves of what I go over here. The first is looking at really spectrum sensing and awareness. So how can we enable our facilities, our devices to be aware of what's going on in the spectrum around them so that we can identify devices, unauthorized devices, threats or jamming or interference that's going on in our networks. We need to need visibility into this so that we can secure all of these wireless systems. And we need to improve our access performance. So as we scale up, we need much better multi-antenna, much better multi-user, and generally much better multi-access efficiency to achieve the performance levels we want in these systems, and to do so power efficiently and with a good user experience, so that your battery lasts longer than a couple hours in these sorts of systems. So I see these as kind of the two core driving problems in wireless, from my point of view. So we've already seen spectrum usage become much more dynamic over the past few years. So CBRS is going live very soon. They're opening up the 6 gigahertz band for Wi-Fi and for private 4G and 5G networks, and so we're going to have even more shared spectrum situations than we do today. And today, a lot of these are much more database driven. So if you look at the CBRS band that's opening up as a shared spectrum, it's much more database driven. So relying on sensing to avoid government users, but then relying pretty much on propagation modeling and communication with a database to authorize licensed and general access users. But I think what we've started to see is, the FCC, for instance, has asked, should we go beyond this? Like, what's the appetite for starting to rely even less on databases and more on sensing in the future as they open up more bands for shared use? And so I tend to think that we're going to see more and more permissive shared spectrum access where, rather than relying on orchestration and databases that we all interoperate with, we're going to start to see more opportunistic sensing, simply because we can pack devices together more densely and use more spectrum. So I think this is one of the also key drivers for, why do we need good spectrum awareness in all of our wireless devices. So if we start thinking about spectrum sensing, there's a bunch of methods that have been used for a long time. So we have tools like energy detection. We have feature-based approaches like higher order moments and higher order cumulants that we can find. We have tools like match filtering for preambles that we can use to do detection. And so there's this collection of, some of them, such as energy detection, are kind of lower complexity, but also lower accuracy. Whereas if we go up to match filtering, the complexity is very high and it's very specific to a waveform, but the accuracy is kind of ideal. under certain channel conditions. And so what we really need is this class of methods, which is accurate, sensitive, low complexity, so that we can actually deploy and use them. And it generalizes well, so we can use this for a wide selection of waveforms and wireless phenomena that we need to detect and understand. So a lot of these previous methods, suffer from either too much computational complexity, being too brittle for reliable use, or being over specialized for only a specific type of waveform. And so machine learning and these kind of deep learning driven sensing tools, I think, are really, really exciting because they move us up in this direction towards very general purpose, very accurate and sensitive, and very low computational complexity solutions that can make sensing actually practical and feasible to use within our devices and networks. And then if you look within kind of deep learning approaches, this is a pretty old graph, but this is showing a number of computer vision architecture definitions. So different neural network architectures used for doing image recognition. And you can see that here we're comparing accuracy to the operation count or complexity. And so this is really the same trade-off that we're looking at over here. But we're continuing to move on this graph, up and to the left to lower complexity and higher accuracy solutions to these problems like image classification or detection in a wireless environment, just by learning more efficient ways to build and structure networks and to train our networks. And so, this is not a fixed location, but it's continuing to move towards the more accurate and the lower complexity space. So this, right. So if we look at the problem of, this was kind of some of the early work we did looking at just signal classification, like assume we have this big piece of spectrum and I want to look at a single signal in the spectrum, and I'm assuming I'm just looking at that one signal already. And I just want to classify what type of signal is it. Well, if you start comparing some of the feature-based methods with a kind of a data-driven deep learning approach with a very simple, kind of a naive convolutional neural network architecture, you can start to see that a pretty trivial approach will give you on the order of 6 dB or more in sensitivity if you look at this kind of accuracy versus SNR curve. So this is really exciting, right? This was exciting to see that we can take such a naive approach, let gradient descent do all of the feature design, and we can get a better solution than we can today using kind of prior feature-based methods, even with very strong decision metrics like boosted gradient trees. So, right, and then also if you start looking at computational complexity, you can do this for lower complexity. And so, these are the really driving features, right? If I can get better sensitivity, I can get lower computational complexity. This makes a ton of sense to do. But RF domain knowledge is still critical in making this work. I mean, you can't just necessarily throw this into a vision network. So there's a lot you have to think about in terms of data, in terms of does the data that you're training on match the data that you want to deploy this on? That being probably the most painful aspect that everyone in machine learning will have to deal with. And so, RF domain knowledge, even if it doesn't go into the network itself, which it can in some cases, but it doesn't have to, really needs to be there in order to do proper data augmentation and proper modeling of what will these signals actually look like when we receive them. How do we model and generate that full distribution of samples? So that's kind of a nice toy problem, modulation recognition. It's gotten a lot of interest over the past few years, but it's not super practical by itself. I mean, if I already know where the signal is and roughly its bandwidth, I've already solved half the problem there. So deciding the modulation between a couple choices is not the full problem. So the full problem, I think, really is this wideband signal detection, and this is I'm given this entire swath of 40 megahertz of spectrum, and it has tens or hundreds of emitters in it, and I just want to know where they all are and what they are. And so if you do this, the traditional method is to take a bunch of FFTs, look at the power coming out of them, and use something like this radiometer-based approach. And if you do some kind of a clustering or a thresholding, you can come up with some energy-based detection metric. And this is great. This is kind of what people have done for a long time to get a very general purpose detector. But if you do this instead using a feature learning based approach, so you're doing pattern recognition directly on the raw RF data to try to do the detection problem, you can actually do significantly better. So if you plot kind of precision and recall curves for the energy-based radiometer, as well as for a kind of a feature learning-based detector, you find out that in some cases this can be 10 dB more sensitive, and so this is huge, and right. So and these results are still under AWGN, which is kind of the worst case for machine learning because it's a whitened distribution. So, and that'll come up again throughout this, is that the problem with most of our model-driven methods is we're assuming all these distributions are whitened, and that's often the worst case because otherwise we could be exploiting more information, right? So putting this all together, we tried to compile all of the best methods for doing this detection and classification of different emissions in the spectrum, using data-driven methods like the ones we just showed, and right. And so this is really exciting now because we can throw in a very complex scene like this with dozens of signals, and within very short timeframes on the order of milliseconds, we can start to identify and classify all of the items in here. So this is exciting because systems that did this before would take seconds or often longer to do these operations by trying to go through and step through all of the possible channels for each one, try to run correlators for them. It's a very painful process to do this using protocol specifics of every waveform that's out there. Right, so I think this is really exciting for kind of the next generation of spectrum awareness, which can be then used in kind of monitoring applications, shared access situations, as well as security. So really providing the view of what wireless activity is in your environment, and then how can you make high-level decisions on that information in real time, so you don't have to deal with this flood of like gigabits of IQ data, but instead you have this nice structured data telling you, what are all the emissions going on in the environment. So if you have that, you can start to do really, really interesting things, right? So we've now turned this flood of signal processing data into a nice structured data problem where we have metadata about all of the bursts and events and emissions and behaviors in the wireless environment. And so we can take this structured metadata, and before it might take a gigabyte of space to record 1 second of that IQ data, but now that same gigabyte could be an entire week of like all of the activity that happened in that band. right? So now we can bring a whole new set of tools and algorithms to bear on these problems. So, now if we have burst counts and statistics about every single wireless emission that's going on, we can start to do time series forecasting and predicting. We can start to use kind of mature CM and monitoring tools that are used today on network side monitoring and analysis. And this is a big deal for security because a lot of these tools, like Kibana, which is shown down here, are the dashboards people already use in security monitoring of wired networks. And so this kind of turns wireless networks into that same level of visibility for people to do this sort of change and anomaly detection across the whole spectrum. So on the right, you can see, these are, we've done this looking at either ISM band or looking at cellular uplink band traffic. So what you see at the top here, I believe is basically ISM traffic density. And so you can see the cycle per day. So during business hours, how much traffic there is. And then if you look at kind of a holiday week, that's all gone. You see maybe someone came in for an hour or two and then it's pretty vacant. So this level of analytics you can now do on kind of every sort of emission that's out there in the spectrum. And there's just a massive amount of information buried behind that. Right, so this is really kind of where I think the sensing side is going. I mean, this can now allow wireless operators to scale their capacity, to even do similar analytics against other carriers, to look at what's going on in the GMR bands and in the emergency bands. I mean, you can really read a whole lot of information about what's going on in an area and in an environment, based on these sorts of analytics on the spectrum. And you can identify things. So do you have rogue behaviors in your environment, people turning on unauthorized transmitters? Do you have failing equipment? All of these things can be seen really, really quickly in this sort of a trace of data over time. So that kind of comprehensive operating picture of the spectrum is something that we really haven't had before. So on the physical layer side, the switching modes from, how do we sense and understand what's going on in the spectrum to, well, how do we actually use the spectrum more efficiently if we're going to be transmitting this data, between our different radios and modems. So, the way that we've kind of always done this in communications is to dissect the problem into all of these pieces of the physical layer. So we look at, our source encoding, our encryption, our channel encoding, how we multiplex this across, time or frequency. How do we do our modulation? How do we do our shaping? So all of these problems, get looked at kind of individually, right? So if we look at our synchronization tools where we're building estimators, we often assume, that we want a map or an MMSC estimator under, typically just a Gaussian channel if we want to derive that from a model in a closed form. If we're looking at channel coding, we're often assuming that we have this binary symmetric channel. If we're looking at our demodulation, we're often optimizing the equalization and estimation under kind of just a linear Rayleigh channel. And if we're looking at the multi-access and the MAC level, we're often assuming something like a Poisson arrival process. These are all just very nice, convenient, compact ways to look at each little piece of this problem. But the problem is these are all wrong. We're not an AWGN. There's more structure to arrival than just Poisson. The channels aren't actually Rayleigh. There's a lot more structure to the distribution than that. And our soft bits into a decoder are not actually binary symmetric. Depending on which bit of a symbol, you can have stronger There's a lot of cases where this is not a true case. So how do we look at this in a different way with machine learning? Well, so we kind of looked at this idea of an autoencoder where rather than build each of these pieces in isolation, assuming a simple model, what if we build a system that does this end to end? So you look simply at this input data and the output data, and then we have a channel in the middle, and you can make assumptions. You can make the same simplifying assumptions in this channel if you want, or you can use real measurement data so that it reflects the full complexity of the real channel you're trying to transmit over. And so this is kind of a new way to look at the problem. So if you do this, and I should say that, think of both this transmitter and receiver as kind of wide open, non-parametric models that can just model any sort of a nonlinear function approximation. So both of these are just kind of neural networks that are trying to approximate some function mapping and then some classification function mapping that outputs this probability distribution over symbols. So we're doing both, and if we learn them both jointly, then we're going to learn some new mapping from bits to symbols, and some new mapping from symbols back to code word probabilities. And then you can learn these jointly. So this is really interesting for a couple reasons. So if you start to look at, well, what if my code words span different sizes? Where does this arrive? So what kind of constellations does it learn? So depending on your channel constraints, these on the bottom left are all kind of possible solutions that it can come to, depending on the constraints. And you wind up with really interesting constellations. Like this pentagonal arrangement is not something that people use today, but it's one that has some very nice properties. And so ML can kind of arrive at these very, very quickly just from random initiation. Right, so autoencoders have been used heavily on the vision side, primarily for compression or for denoising or for finding these kind of lower dimensional latent spaces. But I think that they suit themselves really nicely to these sorts of communication problems as well, because you're just learning a new representation of that information to go over a channel, and you want it to try to learn something that's really resilient in that representation. Right, so if you do this for symbol to bit rates that that match simple approaches like BPSK or BPSK with a Hamming code, you find out that this can very quickly just a very naive approach can attain the same levels of performance that you can expect from similar systems under Gaussian assumptions. But then where this is really interesting is over kind of impairments. So on the right, we have, this is a USRP based system running over the air. And you can see in the middle here, we're running just a 16 QAM signal over it. But at this point in the amplifier, we're getting quite a bit of noise on these outer points, and they're kind of compressing and having more phase noise than you have on these inner points. And so because of that, if you look at this CRC pass rate for these 16 QAM based frames, we're all the way down here to 29% without coding. So this is really degraded, and we're losing packets. Whereas if you start to look at kind of an end-to-end learn system, here we've allowed it to learn and come to a solution uniquely for this channel and for these effects. And so it's come to a solution that's kind of looks sort of like an APSK, where we're using the 0 point in the middle, but we're spacing these inner points much closer and spreading out these outer points to kind of compensate for those effects of the channel. And here, this solution is vastly improved. So we're getting here 75% pass rate over this channel. So this is really cool, because rather than trying to pre-model all of these effects of the hardware, we can let it do this learning over the air and optimize the system in this end-to-end way that's really just using measurement over the channel to try to improve the performance metrics. So try to drive down the bit error rate, in real time by continuing to update how we encode and decode data for that channel. So if we take this as kind of the approach to communication systems, there's tons of ways that we can now think about comm systems. So you can look at multi-input, multi-output system design, learning encodings over multiple antennas and recovering them. We can look at, and there's some really cool work by Dennis Gunduz's group that's looking at this joint source channel coding. And this takes end-to-end even further. So rather than just starting with channel coding, what if we put in pictures or something that has a very non-whitened distribution to begin with, whether it's video or pictures. And so here you can see that if you do that and you try to learn this encoder and decoder, not just for the channel modulation or the channel encoding, but all the way from this image source encoding and decoding, there's even more to gain, because you're combining these non-whitened distributions through even more non-whitened distributions in the channel, and you can just learn a better mapping that more efficiently can handle all of these factors. And so this kind of result here is showing that if you do this, your joint source channel code can outperform LDPC plus JPEG compression by here on the order of 5 to 10 dB in some cases. And so there's a massive amount of capacity left on the table if you look at systems from this approach. But there's also many, many ways to apply this. So looking at multi-user schemes, so non-orthogonal access schemes, looking at ways to help do quantization and channel state feedback, and even things like frame and pilot design and pilot layout within frames, and especially optical systems. So, optical systems are notoriously kind of distortion limited, and so they're very, very ripe for better encodings to take advantage of adapting to that channel model. So I think this is exciting that right now, there's been a few works in each of these areas, but this whole field is kind of totally wide open, and there's tons of really, I think, interesting and fun problems to work on across all of these and more. So how can we get this into real world communication systems? So I want to use this on my phone today. So OpenRAN is something that's going on and that has really picked up massive amount of momentum this year. And so what OpenRAN has done is it's taken this traditional RAN approach where we have a proprietary baseband unit that does the whole L1, L2, L3, typically in some vendor proprietary box. And it's kind of moved it up to this full virtualized RAN where we have standard interfaces between radio units, between distributed units and central units. And then there's open reference implementations for a lot of these. So there's things like open air interface, but there's also, and SRS, but there's also, actual, interchangeable components that carriers are able to start using in their network. And this is really exciting because it makes these pieces of the PHY accessible to R&D. So if we break the 5G network down into this kind of radio unit, distributed unit, the central unit, and then the core, these are now accessible. So you can go get an off-the-shelf radio unit, you can go get an off-the-shelf DU, and you can start actually modifying and experimenting and enhancing some of the algorithms in each of these without having to go and dive into a large tier 1 vendor's proprietary stack that most of them don't want to let you get into, right? So like the Ericssons and the Nokias and the Qualcomms of the world, aren't that open, right? So this is kind of this awesome dream of software radio kind of happening because these barriers are starting to lift, and we're starting to be able to go in and do this sort of algorithmic improvement and test in these real world production systems. So this is really, really exciting also because all of these ideas within these different components of the RAN, we can actually go and start playing with these and trying them out and improving these methods in real world commercial sorts of deployments. And so our focus has really been heavily on the L1 within this distributed unit. So we'll jump through this. So this was kind of some of the early work we did in the L1 within the distributed unit. And this is really interesting. So, we saw some improvements in our kind of Rayleigh and our 3GPP channel models. But we found out that if you run this over the air and you take the G-Node B or the base station and you put basically a learning-based approach to doing all of the estimation, the combining, and the equalization, it can learn more than what the MMSE approach does. So not only do you get this improved performance, but when you start to have these sorts of interference events, if you're able to continue learning what those look like, it can start to do better during bursts of interference. And so again, these kind of non-Whiten distributions, we're seeing on the order of 4 or 5 dB better performance, as it rides through these sorts of interference events. And the other really exciting thing here is that standards don't need to change to do this, right? So we can go do this in today's networks by kind of putting these algorithm changes in transparently. So it doesn't need to be a rapid, wild change to this fully learned autoencoder. You can kind of do it incrementally. It's then interesting to look at in the multi-user system if you have kind of a TDD system with hopping going on across the band. Can you learn solutions that generalize so that multiple UEs can all benefit from jointly learning a better base station uplink solution? And in this case, the answer is yes. We can learn from, in this case, 4 different UEs, jointly. And doing so, you can come up with a better solution than any one individually. And so this actually does scale, right, in a sector that has multiple different channel realizations or different locations, and it can still benefit from learning rather than using kind of the naive model-driven approach. And then if you start applying this to really, really harsh situations, so if you look in the 3GPP spec, you have these heavily defined TDL channel models that are the compliance and the acceptance tests for 5G systems. And so these are very difficult scenarios. So if we look at things like a 1x4 system at 6 dB and 16 QAM, well, you can actually learn a better solution than the MMSE Wiener filtering method here, where you can get almost 3 dB of EVM reduction and 50% bit error rate improvement. And then likewise, these systems, here we're learning a 1x8 receiver solution all the way down to about minus 9 dB SNR with about 2 dB of improvement. So this stuff really works against the harsh channel models that operators have to deal with and test with. So where is this all going? I think there's been a lot of talk about, okay, well, we can do this today with 5G, but what if we want to have this AI native or ML driven end-to-end cellular system? Well, there's a million places where ML can fit into defining, what is 6G or what is this learning driven PHY of the future. We have all these lofty requirements for 6G being orders of magnitude better at spectral efficiency, data rates, power efficiency, number of devices, right? So these are all kind of the requirements that everyone wants. And channel encoding is just the beginning. So we start to look at how is channel state fed back, how are pilots placed, how do we share the access channel? We can look at all of the places that this could fit in. If we scale to ultramassive MIMO, where we have hundreds or thousands of antennas, no longer arranged in these nice uniform arrays. These are very hard problems to try to solve using kind of a direct linear approach. And so you really need better data-driven nonlinear solutions to how do we exploit all these spatial degrees of freedom in a channel, and how do we exploit all of these multi-access and multi-user sharing problems. And really, there's, it's just, the complexity is so high to try to do this any other way that I think if you look at, what could happen, we could have this sort of environmental awareness in every UE. We could be using learning-based channel state feedback in every UE. We could be using, learned encoders and decoders to transmit the L1 information over the RAN from the UE. And then in the Geno B side, we could be learning encodings over very non-standard arrangements of antennas over multiple RUs. We could be again using ML to help suppress interference and nonlinearities that are kind of degrading performance today. And then on top of all of this, we can kind of add this aggregation layer where we can do model sharing and exploiting knowledge across multiple UEs and across multiple base stations throughout a network in multiple regions. So I think, there's still a long way to go to mature all of these aspects of where does machine learning fit into this future ML-driven PHY. But I think there's a lot of really exciting problems here. So that's pretty much it. So, we're growing efforts both at the VT kind of CCI-driven effort as well as at DeepSig. So definitely happy to take questions and always happy to chat and interested in folks that are working in this area. So thanks. That's all I've got.
All right, fantastic. Thank you very much, Dr. O'Shea, for this great presentation. And all the audience, please, if you have any questions, you can either just type in the Q&A, or I know some of you, if you prefer to use the chat, that's also fine. But Dr. O'Shea, let me just start with I think a very interesting talk, very interesting research. Let me just start with a quick question. So I understand you use machine learning, build those data-driven models, right? Now, many of those models, will needs to use existing data sets for the training. And how do you make sure that those models are generalizable? So, for example, you may have a model trained under certain settings, right? Devices, environment. How do we make sure that those models can be applied to, in general, to other settings and systems? Any insights about that?
Yeah, so I think that comes back to 90% of machine learning is data, right? And making sure your data matches the problem that you're trying to solve. And so making sure your solution generalizes is really hard. There's a lot of work to build data sets and to do augmentation. So if you look at, what do they do in computer vision? Well, they build, many terabytes worth of data to try to represent every situation they can. And then they go through and augment, every one of those images into millions of other images to try to represent that image in every other permutation of that image you can. And so we can kind of do the same thing in the spectrum. We need to try to get masses of data to reflect everything that we could possibly think to see. And then we need to use our RF and our propagation and our channel synthesis model to really look at, how do we augment and permute all of that data into even more. And then there's really the problem of monitoring and continuing to improve those systems. So if you look at what Tesla does, anytime a car sees a situation it's not sure about, that gets sent back upstream and added to the data set, right? So, machine learning systems are kind of alive. You need to continue improving them constantly, forever. It's not a nice one-time solution like we're used to.
Right. Yeah, I totally agree. So for example, in the computer vision area, image classification, so they have built this, made a lot of efforts to build the data sets, do the labeling, right? Manual efforts. So there's a question from the audience. If, we have the massive amount of data, but many of them are not labeled, is there a way to do some unsupervised training, in order to avoid the mass amount of, labeling of those data? Is that a kind of a approach that we can try?
Yeah, definitely. So, that's one of the things we've looked at as well. I mean, you can use all kinds of other methods to try to label data, whether it's correlation with known reference tones, whether it's trying to do segmentation based on energy or other features. There's tons of unsupervised methods that you can use to try to curate data and speed up that process of labeling. But also there are, if you look at what people do in computer vision again, they will also put, a billion images on Amazon Turk and get people to label them. There's no one golden bullet to making labeling data easy. There's a whole collection of different approaches to try to do it.
Right. Yeah, I totally agree. So a lot of those communication systems are real time, right? And sometimes if the environment changes, do we need to do some kind of online retraining? For example, those real time retraining of the models. Is there such needs? And if there are such needs, what are the challenges? What are the fundamental problems that we need to address? And how do you validate and kind of revalidate those retrained models?
Yeah, so definitely when you look at comm systems, like, we tried to do online training for all of them. I mean, there's this question of, in wireless, we have this coherence time over which the statistics of the channel are stable, right? And that might only be a couple milliseconds or less in some situations. And so, we have to figure out, are we trying to learn the instantaneous channel? Are we trying to learn a short time distribution that represents that channel? Or are we trying to learn a much longer time aggregate distribution over like maybe what one sector sees for all the different users?
Mm-hmm.
So I think there's a lot of different ways to look at, and there's a really interesting, I think, information theoretic problem in like how much training data do you have over what period of time to arrive at a good solution. And so I think there's some situations that are much more static, like point-to-point links, where you have tons of data to learn at the rate that you need to learn, even specific channel responses. And then you have very highly dynamic systems where that will never be feasible because there's not enough information there, where you need to learn more aggregate distributions that model those dynamics over time. And then the worst case is you get all the way back to, we assume it's Rayleigh, or we assume it's this statistical model because we can literally measure nothing better about that distribution.
Right. Yeah, definitely makes sense. You mentioned that those partnership with industry, for example, NVIDIA really helps. And can you describe a little more? I think this is from one of our audience. Can you describe a little bit more about the relationship and how the industry plays a role, right, in your research? And I think in general, the CCI community is interested in working with industry and the commercialization. Any insights will be helpful.
Definitely. Yeah, I mean, we are always trying to reach out and work with everyone we can. I think NVIDIA, is a unique place in AI right now where they have these extremely powerful GPUs that virtually everyone in the field is using to do their training and test and evaluation on. And so they're kind of a go-to in many ways. But I think, there's a lot of very interesting folks out there. So I mean, I think we've tried to mostly be synergistic with them, helping showcase platforms and capabilities along with our algorithms and solutions. But it varies per vendor. I think it's a lot of that is just kind of relationship building for us.
Right. Yeah, and there's a general question about 5G. We know 5G will make our devices efficient, but is 5G backward compatible? If not, do we have to buy new 5G devices?
So actually, it's interesting what some carriers are doing. If you look at Verizon, for instance, they didn't have new spectrum in the low and mid bands to put 5G on. And so they're doing this thing called dynamic spectrum sharing, which is kind of an overloaded word, but it's what they've called it, where they can run both 4G and 5G on the same base station in the same band and kind of share it. So in that case, you can really, use both to talk to the base station. You're not going to be able to use the newer features or the newer encodings of 5G, without a handset that, supports that protocol. But, it's back to this transparent thing. There's a lot of things they can do, like multi-antenna and multi-user allocations, even within 4G transparently on those same base stations, where you're getting some of the benefits of what 5G helps with, even without using the 5G protocol.
Right. Well, I see there are more questions coming up, and just unfortunately, we are approaching the very end of the 1 hour time window. So I'll take those questions and feed to you, Dr. O'Shea, offline, and then we can share with the audience after that. So with that, very exciting, wonderful talk and the Q&A session. On behalf of CCI and all the audience today, thank you very much for your time, Dr. O'Shea, and we hope that we can invite you back again in the near future.
Awesome. Well, thank you guys for having me. And,
sure.
Always reach out if anyone has more questions.
All right, and thank you very much, everybody, for attending the seminar today. It's really a wonderful experience having this seminar, CCI seminar series. It has been very successful in this semester. And as you know, that this is the very last lecture in this series. And but stay tuned, right? In the next semester, in the spring, we're going to start a new seminar series, which is about the human aspects of cybersecurity. So we are looking forward to new exciting talks in spring. All right, thank you very much again, and I wish everybody have a great day. Thank you.